So it is convenient to describe a sequence with a formula, and we can also call it as explicit formula or the general formula. So an explicit na formula or general formula for a certain sequence is a rule. And this rule shows how the value of each terms a sub k will depend on k. So for example, the sequence on the previous example that I have given you may be specified as a sub k, where a sub k is equal to 2 raised to k. So we have the terms a sub 1, a sub 2, a sub 3, a sub 4, okay? So, and we know that a sub k is equal to 2 raised to k. So if the value of k is equal to 1, so a sub k will be equal to 2 raised to 1. If the value of k is equal to 2, then the value of a sub k will be equal to 2 raised to 2. So again, the values of each term a sub k will depend on k, right? So suppose we have this explicit na formula a sub k equals 3k, okay? So what will be the terms in the sequence? So the terms in the sequence will be a sub 1, a sub 2, a sub 3, and so on. So how can we determine the sequence based on this explicit na formula? So what we are going to do is basically substitute the value of k into the general na formula. Okay, so again, we have mentioned that the value of this term will depend on the value of k. So if the, suppose we have this a sub 1, a sub 2, a sub 3, so we respectively substitute these values to k. So we obtain then 3, 6, 9, and 12. So where did we get this from? So we have 3 times 1, assuming that the value of k is equal to 1. So that will be 3 times 1. So if the value of k is equal to 2, that will be 3 times 2. If the value of k is 3, that will be 3 times 3, and so forth. So note that this sequence is indexed from 1. However, in some textbooks, they start with 0 or some other na indices. Okay? So suppose we have a sequence a sub 1, a sub 2, a sub 3, and so on. And another sequence b sub 2, b sub 3, b sub 4, and so on. So what do you notice from this sequence? So this sequence starts from, the index starts from 1, okay? And the other sequence starts from 2. And we have this explicit formula, a sub k equals k divided by k plus 1 for all integers that are, for all integers k that are greater than or equal to 1. Okay, so we these terms a sub 1, a sub 2, a sub 3, and so on may be computed from this explicit na formula. Meanwhile, for this sequence b sub 2, b sub 3, and so on may be computed from this explicit formula b sub I equals 1, I minus 1 divided by I for all integers I greater than or equal to 2. So we then have this value for each term. The a sub 1 will be equal to 1 divided by 1 plus 1. So we simply substitute 1 to the explicit na formula. Okay, so we then have 1 over 1 plus 1, which is equal to 1/2. For a sub 2, so we simply plug in 2 into this formula, and so on until we form our sequence. So we have term 1, a sub 1, it's 1/2, term 2, a sub 2 as 2/3, and so on. Meanwhile, how can we obtain the value of the sequence b sub 2, b sub 3, and so on? So we simply plug in each value of I into this formula, I minus 1 divided by I. So we have b sub 2 Why did it start with b sub 2? Because we have this restriction wherein the integers are greater than or equal to 2. So we have 2 minus 1 divided by 2, and then plug in for b sub 3. So plug in 3 to this formula. So we have 3 minus 1 divided by 3, and so on. Okay, so now another example. We write the first 4 terms of the sequence that is defined by the formula b sub j equals I plus 2 raised to j for all integers j greater than or equal to 0. So what would be the solution? So basically what we do is determine the terms. So we have b sub 0, b sub 1, b sub 2, and b sub 3. Since we have a restriction here that the integers j is greater than or equal to 0. Okay, so we simply, for each of this k, we substitute it into the formula I plus 2 raised to j. So we have, if j is equal to 0, we have 1 plus 2 raised to 0, and it will be equal to 2. If j is equal to 1, we have 1 plus 2 raised to 1 equals 1 plus 2, and that will result to 3, and so on. Okay, so we form a sequence 2, 3, 5, 9, and so on, and so forth, based on the explicit formula that was given. Okay, so again, the formula for all integers j, the formula b sub j equals 1 plus 2 raised to j for all integers j greater than or equal to 0 will then define an infinite sequence having infinite number of values. Now, let's have another example. So what we want to do is to compute the first 6 terms of the sequence that is defined by this formula. So we have c sub n, and c sub n is equal to 1 plus negative 1 raised to n. So note that the negative is included for all in the parentheses, okay? For all integers n greater than or equal to 0, okay? So what would be the solution? Again, we determine the terms. So we have c sub 0, c sub 1, c sub 2, and so on. Since we have a specified the restriction here wherein the n is greater than or equal to 0. So it starts with c sub 0, and so on. Now, for each of this value of for each of this k, we plug that into the explicit formula 1 plus negative 1 raised to n. Okay, so if k is equal to 0, then we have 1 plus negative 1 raised to 0, and that will give us a 2. And if n is equal to 1, then we have 1 plus negative 1 raised to 1 equals 0. And what can we notice about this sequence? So this sequence is actually alternating, right? So because we can see that the first 6 terms are 2, 0, 2, 0, 2, 0. Okay. So it follows that the sequence oscillates endlessly between 2 and 0. Okay. Now in the next the slide. So what we want to do now here is to compute the first 6 terms of the sequence c sub 0, c sub 1, c sub 2, and so forth, defined by the following formula. So c sub j is equal to negative 1 raised to j for all integers j greater than or equal to 0. So again, we simply plug that in each of the value of k. We plug that into our formula. So we have negative 1 raised to 0, and then negative 1 raised to 1, and then negative 1 raised to 2, and so on. So what do we notice here again? So this is basically a similar example to the previous slide, where in the sequence, is also an alternating sequence. So in this case, the sequence whose terms alternate in sign is called as an alternating sequence again. So in the next slide, we are going to find an explicit formula to fit given the initial terms. So what we did in this previous slide, in these previous examples, was to determine the sequence based on the formula that was given. So in this case, we are going to find, given the sequence, we are going to find an explicit na formula. All right. So